Chapter 2: Tokenization. Before a model can do any math, it has to turn your text into numbers. This is the very first step of the pipeline, and it shapes everything that follows. Let's see how words become numbers. Here is the problem. A neural network only understands numbers. It cannot read the letter A or the word cat. So the first job is translation. Take a string of text and break it into a sequence of small units called tokens. Each token will later get its own number. A token is simply a chunk of text the model treats as one unit. That is the word to remember, token. But how big should a token be? Option 1: 1 token per word. Clean, but the vocabulary explodes, millions of words, and any new or misspelled word breaks it. Option 2: 1 token per character. Only a few dozen symbols, but now even a short sentence becomes a very long sequence, and single letters carry little meaning. Both extremes hurt. So real models pick something in between. The answer is subword tokens. Common words stay whole. The cat and sat are each a single token. But a rare word gets split into familiar pieces. Take the word tokenization. The model breaks it into token and ization. Two pieces it has seen many times before. This way, a small vocabulary can still spell out any word, even one it has never met. So how does the model decide where to split? With an algorithm called byte pair encoding. It starts with plain characters. Then it scans a huge pile of text and finds the most frequent pair of neighbors. Say the letters T and H appear together constantly. It merges them into a single unit, TH. Then it repeats, find the top pair, merge it thousands of times. The frequent chunks become tokens, the rare ones stay in pieces. Once the token list is fixed, each token gets a number, its ID. The vocabulary is just a lookup table, token on the left, integer on the right. The becomes 464, cat becomes 3797. So our sentence, the cat sat on the mat, turns into a row of integers. That row of numbers is what actually enters the model, text in, numbers out. A couple of things worth noticing. Token count is not word count. A common word is 1 token, but a long or unusual word may be 3 or 4. Spaces and punctuation usually ride along inside tokens too. And this matters in practice. Models have a context limit measured in tokens, and you are billed per token. Fewer tokens means cheaper, faster, and more room to think. Here is what it looks like in real code. We call encode on our sentence, the cat sat on the mat, and get back a list of 6 token IDs. Each number is 1 token, straight out of the vocabulary. And crucially, it reverses. Call decode on those same numbers and you get the exact original text back, character for character. Tokenization is a perfectly reversible dictionary between text and numbers. So, tokenization. Text is chopped into subword tokens, and each token maps to an integer ID. Not too many, not too few, a balance learned by byte pair encoding. Those integers are the model's real input. But an ID is just a name. Next, we give each token meaning as a vector. Chapter 3: Embeddings.